IOE 413 Radiation Therapy Planning Study Guide. This question asks you to formulate both the full primal and the reduced primal problems for radiation therapy planning. And this is a slightly different example than what was in the notes, because instead of a 3x3 matrix, there's a 2x2 matrix of voxels. And what we can see in this example is that there's one tumor. Okay, so this is one tumor voxel, and the rest are normal tissue voxels. And then we have 8 beams, and this time the beams are aligned a little bit differently because there isn't a middle row here as there was in the notes for voxels. There's just 2 voxels above, 2 below, 2 to the right, 2 to the right, and 2 to the left. These beams, like beam 1 and 5, split in the middle here. And half the dose is going to go to the upper voxels and half to the lower. And then beam 3 and 7, half are going to go to the left and half to the right. So let's look how that works. The weights for beam 1, here is beam 1. It's going to say that 0.3 of that weight of beam 1 is going to be absorbed by the tumor voxel 1 up here on the top. And then in the bottom, for voxel 2 of the normal tissue, voxel 2 of the normal tissue is also going to be 0.3. So we'll have 0.3 above, 0.3 below. And then there'll be some more radiation that will pass through to voxel 1 of normal tissue. Voxel 1 normal tissue accepts 0.1 of the beam weight. Voxel 3 below takes 0.1 of the beam weight. And then there's some radiation that's going to pass all the way through. It won't be absorbed by any of the voxels. Now the diagonals are a little bit more complicated. Take beam 2. Beam 2, this first voxel, the closest one, voxel 2 of the normal tissue, voxel 2 in the normal tissue for beam 2 will absorb 0.4 or 40% of the weight of beam 2. And then on either side here, basically this beam is going to cut through just the corners of these tumor voxel 1 and normal voxel 3 here. So if we look, tumor voxel 1 accepts only 5% or 0.05 of the beam weight for beam 2. And voxel 3 of normal tissue down here accepts 0.05 or absorbs 5% of the beam weight 2. And then the beam weight 2 continues on to this other diagonal voxel, voxel 1 of the normal tissue. And we'll see voxel 1 of the normal tissue takes and accepts 15% or absorbs 0.15 of the beam weight. And that pattern holds true for all these different beams. The horizontal and vertical beams here, 1,5 and 3,7, basically split their radiation evenly between either side and pass less through. And that's given in the table down here. And the same thing for all the diagonal beams, 2, 4, 6, and 8. So that's the basic statement of the problem. So let's recall that this is the statement of the full primal model formulation for radiation therapy planning that we covered in class. You'll notice that what we need to define here is C, A sub T, A sub N, X superscript U, X superscript Y, and Y superscript U. That will be sufficient to define the model. Let's begin by defining A sub T, which you see written down here. Well, how do we get A sub T? Well, A sub T is what transforms the beam weights to the tumor voxel dose. Remember, there's just one tumor voxel in this problem. It's up here in the upper left-hand corner. And if you look at what it absorbs from beam 1, we look here at beam 1 to the tumor voxel, and the tumor voxel absorbs 0.3. That's the 0.3 that's right there. Now let's look at beam 2. Beam 2 contributes to tumor voxel 1. Beam 2 contributes to tumor voxel 1, 0.05 of its weight. That's what we get there. Okay? Beam 3 comes up from the bottom. And let's see, beam 3 contributes 0.1 to tumor voxel 1. That's right there. Okay, and we can continue like that. 0.15, okay, 0.1, 0.05, 0.3, and 0.4. And that is how we get our A sub t. It is just this column in the grid that I gave you in the study guide defining the contribution of individual beams to voxel 1 of the tumor. Now let's construct the A sub n matrix. And A sub n is the matrix that transforms beam weights to doses in the normal tissue voxels. And let me just outline here those 3 voxels that are normal tissue. And this one up the upper right is normal voxel 1, just to remind you. Because that's where we're going to start. We're going to start with the first row of A sub n. We look to see how much beam 1 contributes to the dose in normal voxel 1. And as you see here, beam 1 contributes to the dose in normal voxel 1 by 0.1. And that's what we get right here. Okay, beam 2. Beam 2 contributes 0.15 right here. And that's 0.15 here. And you can see as we go through this entire column, this column becomes the first row. Okay, so this column becomes the first row. Similarly, if we look at the voxel 2 of the normal tissue, that's the second row of A sub n. We look to see how much beam 1 contributes, and we look to see beam 1, it contributes 0.3. You can see 0.3, and you can already see the pattern emerging that, in fact, the second row of A sub n is, in fact, just this column of the grid where we presented the absorption data and the statement of the problem. And finally, the third row of A sub n is this column. Let's do the upper and lower bounds. So as you'll recall, x is bounded above by x superscript u. Is bounded below by x superscript l. Y is bounded above by y superscript u. So let's look at the bounds here. Well, there's only one tumor voxel, and x is the vector of doses to tumor voxels, so x is just going to be a scalar. So we're going to write x sub u is the upper bound for the dose to the tumor voxel, and that would happen to be 200. The lower bound, x superscript l, is 75. And then the upper bounds on the normal tissue voxels are given right here. So y superscript u is just the 3-element column vector of 10, 10, and 10. So recall that this is the mathematical formulation of the full primal formulation. And the objective function, as you'll recall in the full primal, okay, is we want to minimize the total dose of radiation going to normal tissue. Okay, so we need to sum the dose over the normal voxels, and that's y1 plus y2 plus y3. We could write that actually in matrix form as E transpose y. Okay, but then the question is, how do we have to define C in order to make the objective function be this? We have to construct C somehow so that when you do C transpose W, that's absolutely equivalent to E transpose Y, or Y1 plus Y2 plus Y3. So let's do that. So let's figure out what C needs to be. The easiest way to do it is to say, well, we know that we want to minimize the objective function being E transpose Y. That's the total dose given to the normal voxels, okay? But we need to rewrite that somehow as C transpose W. We need to figure out what C needs to be to make it so that when we minimize C transpose W, we're actually minimizing E transpose Y. Well, let's recall from the basic physics of it that Y is equal to A sub n times W. A sub n is the matrix that transforms the vector of beam weights into doses in the normal voxels. Well, let's just substitute that in right here on the right-hand side. So we get E transpose A sub n W on the right-hand side. We have C transpose W on the left-hand side. Look at that. We got W there. We got W there. So look at this. If we just said that C transpose is equal to E transpose A sub n, we'd be fine. We would have what we want. Well, we really want a C instead of a C transpose, so let's transpose both sides. And what that gives us is C is equal to A sub n transpose times E. And that just happens to be what we have up here. So C equals A sub n transpose E, and this is our A sub n transpose E, and this is our C vector. We are now ready to write down the answer to part A of this question. So we want to minimize, and this row vector there is C transpose, and this matrix here is A subscript T. This matrix here below is A subscript N. This is our upper bound on the tumor voxel dose, X superscript U. And this is our lower bound, X superscript L. And this is our upper bound on the doses to the normal tissue voxels. So this is Y superscript U for upper bound. And that is our full primal model for the radiation therapy problem. Now let's do part B of this question. What you see here is the reduced primal form of the model. All we need to do now is take the numerical matrices that we've already defined and put them into this form of the model. So we can write down the answer to part B. And this row vector up here on the objective function is C transpose, as before. This vector that transforms beam weights to tumor voxel doses is A sub T. Now this matrix here is A sub n. Okay, and the right-hand side over here is Y superscript U. And then we have X superscript U. We have X superscript L. And that is the statement of the reduced primal model for the data that are presented in this question.